let me write it here, okay, such that H composition inclusion map from X into X union Y is equal to F, and H composition inclusion map from Y into X union Y is equal to, what is that other map? G. So this is the exercise. So we now solve the parts one by one. First of all, we have to prove this. These are not very difficult, only the notation looks intimidating. Okay, so in the first one, subdivision A, we have to prove this, right? Let me just write it for once. From Y into Z, composition inclusion map from X into Y is equal to inclusion map from X into Z. And it is given to us that X is a subset of Y and Y is a subset of Z. So note that since X is a subset of Y, so this inclusion map makes sense. Just like that, since Y is a subset of Z, so this inclusion map makes sense. And since these relations imply that X is a subset of Z, this inclusion map makes sense. Okay. Now, now we don't have to write the maps again, I mean, to show that their domain is this and range is this, because the domain and range are both written for each map below them, below the symbol. So if we look at this map has range Y and this map has domain Y, and they are equal. So that means this composition makes sense. And the composition will have domain X and range Z. This map also has domain X and range Z. So the first condition for equality is true in this case. So let us just write that. Note that both this map and it's not that long, okay, it should be short. And first of all, we have Y into Z, then we have X into Y, have domain X and range Z. Let X belonging to X be any element. Okay, so what we do, we just basically apply this, because the inclusion map definition is very easy. It's the rule of assignment is just like the identity map. Then, so we directly calculate the image of this map. Oh, I said image, I mean output of this map when the input is X. So by definition of composition, this is equal to, this is looking like L. Okay. Now, the inclusion map from X into Y includes X inside Y. So, anyway, this maps X into itself. So, the output is nothing but X. Okay. Now, note that since X is an element in X and capital X is a subset of capital Y, so X is an element in Y also. So that means we can apply this map on X, and this is nothing but again X, and this X is also the output of this map when the input is X. So that's it. This implies so this is the solution to the first subdivision. Then comes the second. In the second one, we are asked to show this. Composition. No matter how hard I try, I seem to not be able to remember this thing. Okay, so this is the one we have to prove. So let us first of all quickly see the things. The domain of F is, let me just write it below the symbol F. Domain, for this function domain is A, range is B. For this one domain and range are both equal to A. So the range of this is equal to the domain of this. So this function composition makes sense, and it maps again A into B. So this function, this is a function from A into B. And what about this one? Here again, okay, now here the range is B, here the domain is B, they are equal. So this composition also makes sense, and it maps again A into B. Domain of the first map from the left into the range of the map on the right side. Domain of this one, and range of this one. Okay, so both these are mappings from A into B. So that's what we mentioned first of all. So the pattern here is also just like this one. Note that all the three maps or functions, we have already mentioned that maps, transformations, functions, these things are used synonymously. Maps, F, then F composition, this, and have and range B. Let A belonging to A be any element. Then first we calculate the output of this function when the input is A. Since this is the the identity map, so this is nothing but A. FA. Also, now we calculate this one. Okay, now since A is any element in A, so FA is any element in B in the set B, and this iota B into B is the identity map on B. So it maps FA into onto itself. Okay. Thus, and now we can conclude, because the image, I mean the output of this function matches with the output of F, and same is the case with this function. Its output also matches with the output of F. So thus, F is equal to this. So this completes the second subdivision. Now the third one. C. So what does the third one ask? Show that if F from A to B is a bijective function. Okay. If F from A to B is bijective, then we have already proved this in one of the previous exercises, that actually, we can mention that actually if we want to be specific, then by exercise number 336, the sixth one, we have, okay, let us recall what we had there. F inverse F of A is equal to A for all A belonging to A, and F of F inverse of B is equal to B for all B belonging to B. Okay. This implies how can we write this? We can write this as F inverse composition F of A is equal to, in place of A we can write this, for all A belonging to A, and similarly this is F composition F inverse of B, and this is equal to this. Hence, by the definition of equality of functions, F inverse composition F is the identity map on A, and F composition F inverse is the identity map on B. Okay, so this is the third one, and finally the fourth one. Okay, so for the fourth one we are given two functions. What are we given? We are given two sets, X and Y, which are disjoint. It's better to draw a diagram it looks like this. This is x and this is y. Since they are disjoint, there is no common element. And this is z. Now here we have a function f from x into z and a function y, a g from y into z. We then have to prove that there exists a function h from x union y into z. And what is the property of h? H has to satisfy these equations. Okay, so let us start. And h is the only function, it's the unique such function that satisfies these equations. That uniqueness also we have to prove. So let us first of all show that there exists at least one such function, h. Okay. We are going to straight away define h. By hx is defined to be equal to fx if x is in x and equal to gx if x belongs to y. Let us first take some moment and see whether what we have defined it makes sense or not. If we take any element in x union y, say any element x, for this function to be well defined, this x should have a unique output in z. According to the definition of this function, hx is defined to be equal to fx if the input is in x and defined to be equal to gx if the input is in y. Now note the fact that this x will be in either capital X or capital Y. Being in their union, it will be either in X or Y. But this is important that it cannot be in both X and Y because X and Y are disjoint. So it will be in exactly one of them. For a given X, that X is either in X or in Y but not in both of them because they are disjoint. If X belongs to X, then the definition says that the output is fx. And since f is a function from x into z, so this fx is a unique element in z. If the input belongs to y, then the output is gx. G is also a function from y into z, so the output belongs to z and is a unique element in z. So this function is well defined. And of course we are not going to say so much, we will just say this much. Since x intersection y is the empty set, h is well defined. Okay, now we have to verify these equations. Okay, so next observe that what is the range of this function, this iota of x into x union y, and what is the domain of h, x union y. They are equal, so that means this composition makes sense, and this composition has domain x and range z. F on the other side of this equality, f also has domain x and range z. Observe that both the functions and F have domain X and range Z. Now we have to show that they map the one element onto the same thing in Z. Let X belonging to X be any element. Then we straight away calculate the output. This is equal to since this is nothing but the inclusion map, the output is X. But keep in mind that this X is coming from capital X. So according to the definition of H, this Hx is nothing but Fx. Hence, since we have shown that this is true for any x in X, y is equal to F. Next we prove this one. This is also similar, and in fact I am not going to prove this one. I leave it to you. Similarly, show this. Okay, so based on the assumption that you have shown this one, we are now next going to prove that this H is unique. Okay, so let H, let me consider K, let K from X union Y into Z be any function such that K also satisfies these equations. If we replace H by K, we get the same thing. This is equal to F and is equal to G. Our goal is to prove that H and K are actually equal. See, the first thing is that both H and K have, H is this specific function, okay, which has been defined using F and G. K is any function with domain X union Y, range Z, and satisfying these two equations. It can be any function, but we have to prove that it is nothing but H. So already H and K have the same domain X union Y and the same range Z. So it's enough to just show that they match in terms of mapping the values of the domain or the values of the range. So let X belonging to X union Y, the domain now is X union Y, be any element. Now exactly two things will happen. Either X belongs to X or X belongs to Y. Accordingly, there are two cases. Assume X belong to X, then what? K composition x is equal to fx. Now this is true for any element in x union y, not just this case, but for in particular for this case we are going to see now what this implies. So this implies this is equal to fx, and this implies, since this is an inclusion function, this is nothing but this. Okay, now we look at the second case. Next, assume that x belongs to y. Then we are going to use this one. Now this is y. Oh, I think right now I said that this is true for any x in x union y. No, that is not true. This is true only for elements in x, because if the element is not in x, then the right hand side would be meaningless. Okay, so this can be applied only for this case, and this can be applied only for this case. And what does this imply? Similarly, gy k of I, the hell I wrote y, x, kx is equal to gx. So what have we shown? That is, kx is equal to fx if x belongs to x. When x belongs to x, kx is equal to fx. And when x belongs to y, kx is equal to gx. And if you recall, this is nothing but the definition of the function h. Hence, k is equal to h. This proves the uniqueness of h. So, first of all, we have shown that such a function h exists, and then we have proved that this is unique. So, here the exercises to section 3.3 end. So, after this, we are going to go back to ring theory. And once a significant portion of, we are going to start homomorphisms, kernels, those things of rings. And once a significant portion of that is over, we will come back to it. Of course, after this, I think we have Cartesian product or something like that is there. So we are going to see that. So with this, I end this video. If you are new here, please subscribe to my channel. It helps me out a lot. So that's all for this video. So this is Lucifer signing off from the mathematical room. Have a nice night.